Take a look at the physical objects in your immediate reach. The food you consume, the clothes you wear, and even the pages of an old book all share a single foundational element: carbon. Carbon forms the basis of all living structures and millions of unique compounds, making it easy to assume the element is abundant. But as we pull back to view the Earth, a strange statistical paradox emerges. This chart shows that the Earth's crust contains only 0.02% carbon in the form of minerals. Our atmosphere holds even less, with carbon dioxide making up a mere 0.03% of the air. This creates a massive disconnect. How does an element with such a meager physical footprint serve as the building block for millions of distinct substances? Carbon's ubiquity is driven by the specific physical architecture of the atom itself. To understand how these structures form, we have to look past the standard ionic bond model. Usually, elements achieve stability by fully gaining or losing electrons to fill their outer shells. But carbon compounds don't behave like ionic substances. They are poor conductors of electricity and possess relatively low melting and boiling points, suggesting their internal connections are built on a different logic. With an atomic number of 6, carbon has 4 valence electrons. Gaining or losing 4 entire electrons would require a massive energy investment or result in a highly unstable atom, making the traditional give and take of ionic bonding impossible. Because carbon cannot use the standard rules of exchange to reach stability, it utilizes an entirely different mechanism to survive. This diagram shows carbon's elegant solution, the covalent bond. Instead of giving or taking, carbon secures its shell by sharing its 4 valence electrons with other atoms. We can see this in methane, the simplest carbon compound. A central carbon atom anchors 4 hydrogen atoms by overlapping its electron clouds with theirs. This sharing arrangement keeps the outer shells of every involved atom satisfied. Because no electrons are fully transferred, no charged ions are formed. This ability to form 4 distinct covalent bonds simultaneously is known as tetravalency. Tetravalency transforms the carbon atom into a multidirectional hub capable of connecting in endless configurations. This visualization shows catenation, carbon's ability to form covalent bonds with other carbon atoms. Catenation allows for massive structural diversity. These chains can remain straight, branch out into complex webs, or fold into closed rings. The lengths themselves can vary. Saturated compounds rely on stable single bonds, while unsaturated compounds utilize reactive double or triple bonds between atoms. We can modify these chains even further using the homologous series. By replacing just one hydrogen atom with a functional group, like an alcohol or an acid, the entire compound's properties change, regardless of how long the carbon chain is. From the fuels that power global industry to the medicines that save lives, we rely on the incredible versatility of carbon compounds. This complexity is not a product of abundant resources, but of atomic efficiency. The necessity for a carbon atom to share its 4 electrons creates a domino effect of modular architecture that literally builds our world.